discussion again. So we had said that if R is a ring and I is an ideal, then R mod I, which contains all the elements of the form R plus I, so that R is in R. This is along with the operations were defined as R plus I plus R prime plus I would be R plus R prime plus I and R plus I, right? So this was the definition, if you recall, right? Some examples which can be studied immediately is that you can observe that Zn, you can think of Zn as Z mod the ideal generated by n, right? Because if I talk about Z mod the ideal generated by n, then what should the elements look like? Okay, if you carefully observe, then the elements should be looking like of the form A plus n, right? Such that A is in Z. Okay, but in that case, you can observe that the element should typically be of this form, right? So it should be, rather, I should say, yeah, fine, fine. This will do typically. So can I, in some sense, conclude that there will be elements corresponding to 0, 1, 2 till n minus 1. Okay. So if you carefully, in some sense, if you carefully observe this group, actually, see, discussing this purely in terms of set theory, it's a bit difficult and complicated. Rather, you can actually think of these elements in this way. You can think of the element 0 plus n, you can think of the element 1 plus n, and you can keep continuing. Because something you can observe is that you will reach n minus 1 plus n, but then you will reach n plus mod n, but that will be 0, or rather similar to 0 plus mod n, right? Since n is in 0. Uh, sorry, since n is in the ideal generated by n. Similarly, you can observe that minus 1 plus mod n, ideal generated by n is same as n minus 1 plus the ideal generated by n, right? So the number of distinct terms should be these. So basically, it will only contain the elements x plus n such that x equal to 0, 1 till n minus 1. So there is in fact a set theoretic correspondence which we can observe, right? Uh, this sort of an equality, this is indeed not an equality because there is no element wise similarity, there is only a behavioral similarity. So they are basically isomorphic to each other. Okay, and we will get a better notion of this isomorphism a bit later. But let us first understand a few important examples of quotient rings. Fine. So as I had said previously, that most of our discussions are developed in order to have a better analysis of the rings of polynomials, right? So this example, let's consider let R be the polynomial over a field. Okay, F is a field. Fine. Now let I be the ideal generated by some Px. Okay, Px is some polynomial in Rx. Okay. So therefore, by definition, I should be of the form fx times px such that fx is in Rx. Fine. Now observe that now if gx is an element of fx, fine, then we know that I can divide g by p, right? Then I can write gx as qx times px plus Rx. Okay, we had already proved this up such that, and since we are talking inside a field, so this factorization is in fact unique. So what more we have such that R is either identically 0 or the degree of R is less than the degree of P, right? Here we are dividing by P and not by Q. I am talking about division by P, dividing by P. Yeah, okay. Now observe that then what should be Gx plus Px? What should this look like? So this is exactly equal to Qx Px plus Rx, right? Plus the ideal generated by Px. So this is basically equals to Qx Px plus the ideal generated by Px plus Rx plus the ideal generated by Px. But then this element is inside the ideal generated by Px, right? So it will collapse to simply the ideal generated by Px, or rather 0 plus the ideal generated by Px, right? Plus Rx plus the ideal generated by Px. Right? So what does this imply? This implies that Rx, so this becomes that Gx plus Px, therefore Gx plus Px, the ideal generated by Px is basically Rx plus the ideal generated by Px, right? So what does this immediately mean? Okay, so this basically means that the elements, therefore, uh, fx mod px, this should consist of elements of the form fx plus the ideal generated by px, such that either f of x is 0, the 0 polynomial, or the degree of f is less than the degree of p. Yeah. Okay. Fine. And we can obviously say about this because we had already proved previously that this factorization is unique. Okay. In that case, we can also say that each of these representations will be unique inside the quotient group, quotient tree. Yeah. Okay. Okay. Fine. So we need to keep this in mind that whenever we are going to talk about a quotient ring in the polynomial field with the ideal generated by a single polynomial, then what we need to have in mind that the elements should be the collection of all those fx plus ideal generated by px elements where fx has degree less than the degree of p or fx is identically 0, right? Okay, fine. Let us consider a better example and a numeric example for say, suppose you say your f is the real numbers and you choose px to be x square plus 1. Okay, then then rx mod x square plus 1, right? This should be collection of all the elements of the form ax plus b plus x square plus 1 such that a and b are real numbers, right? Right. Now observe that. Now if I consider the multiplication of two such elements, okay, the addition is pretty obvious. Why am I considering multiplication? Because if you consider the multiplication, then the degree will be, in some sense, it might be equal to the degree of the polynomial which is generating the ideal, right? So observe that if I multiply ax plus b plus x square plus 1 with say cx plus d plus x square plus 1, then we would what we would be getting? We would be getting x plus b times x plus d plus x square plus 1, right? So this will give me ac x square plus ad plus bcx plus bd plus x square plus 1, right? But this term has to be collapsed in some sense, right? So observe that since we are doing so, since we are in some ring modulo I, so the elements of I in some sense, you can just take it to be very literal in sense that the elements of I must collapse to the unit, collapse to unit, right? In that case, what I mean to say is that the element x square plus 1, this is inside the ideal generated by x square plus 1. In this case, if I talk about this example itself, so this implies that x square plus 1 is equal to 0 in the quotient tree, right? That means that x square is equals to minus 1 in this quotient tree. That's exactly what I meant to say, right? Therefore, I can replace x square by minus 1. Getting my point? Fine. So this becomes minus ac plus ad plus bcx plus bd, right? Therefore, there is no problem in calculating the multiplication. I hope you got the point, right? So whenever you will be getting elements, inside some ideal generated by some element of a ring, and you take the quotient ring with respect to that ideal, then the element which is generating the ideal, or the elements which are generating the ideal, you need to keep in mind that they are actually representing the zero element inside that ideal, inside that quotient ring. Okay. Now the reason why I chose this example is very important. Okay. Observe. Observe. Okay. See. So reconsider Rx, Rx upon x square plus 1. So this is the collection of all the elements ax plus b plus x square plus 1 such that a and b are in R. And what we just saw is the following, that for every ax plus b plus x square plus 1, cx plus d plus x square plus 1. Okay, let me slightly write it in a different notation. You will understand that why I am doing so. Okay, let me write it as a plus bx. Okay, a plus bx, c plus dx. Okay, their product is so a plus bx plus x square plus 1 times c plus dx plus x square plus 1. So this came out to be ac minus bd plus bc plus ad x plus the ideal generated by x square plus 1, right? Okay. So now observe. So this is something which we can observe, right? This is something which we just now did. Okay. Now, what we can do is that now see that if a plus bx is in or a plus bx plus x square plus 1, if I consider, then uh, a plus bx plus x square plus 1 times, if I do this element, say a by a square plus b square minus d by, sorry, minus b by a square plus b square plus, okay, with this with x plus x square plus 1, what we will be getting. Okay, so in terms of this calculation, I will be getting this to be 1 plus x square plus 1, right? So you will get AC minus BD, right? So you will get A times C minus B times D. So it will become 1, right? Getting my point? Another part will become 0. Therefore, every element in Rx mod x square plus 1 is a unit, right? Every non-zero element is a unit. This means that this quotient ring is actually a field, Yeah, got it. And there's a very interesting thing to observe here. Consider the map. Now this is the reason why I wrote it in a different notation. Consider the map phi from Rx by x square plus 1 to C such that we map the element a plus bx plus I to a plus bi. Okay. Then you can observe immediately that this gives a ring isomorphism. In fact, this is a field isomorphism. This is an isomorphism of fields. Both of these are fields. Okay, this is a field itself, this is a field itself. Yeah. So basically, this iota, this iota I, it actually corresponds to, as I said previously, if you recall that we had said that, let's just go back a bit. I guess in the first page, right? Yeah. Here we had seen that x square plus 1 is a number, or it is basically 0 in the quotient ring. So x is a number whose square is negative 1 in this quotient ring. So this x is itself identified by iota. The element x is actually identified by iota. Yes. There is actually one more way of getting hold of this, which is the following, actually. Okay. So consider a map phi from, yeah, so what we can do is basically, what I'm trying to do is basically that, or rather, let me not discuss it here itself, but there's a way to take a map from Rx to C in such a way that the kernel of phi will come out to be x square plus 1. This map will be, so what we can do is that we can map x to I. Yeah, we can map it to x to I. Okay. Okay, once I map it to x to I, then we will see that the kernel will come out to be every polynomial which is a multiple of x square plus 1, right? Because the minimum degree polynomial, px such that the p of I is 0 is x square plus 1. Okay, see, this evaluation is, I'm doing this on the basis of this. Okay, see, so I'm mapping x to I, right? So what I'm typically doing is that I am choosing a polynomial fx and I am evaluating it at I. Okay, this is the thing which I'm trying to do. Okay, fine. Now once I do this, what should be the kernel of phi? The kernel of phi should be the collection of all f of x such that f of I is 0. Okay, but this, if you study introductory field theory, or I'll try to come up with a more rigorous proof of this, that x square plus 1, this is the minimal polynomial for I. In other words, if f of I is equals to 0, then that implies that I can write f of x as x square plus 1 times g of x. That's exactly what I mean. So every element in the kernel is some multiple of x square plus 1, and x square plus 1 is irreducible. That is, we have not yet introduced the term of irreducibility, or I don't remember whether I introduced or not. But x square plus 1 can't be reduced into factors of lower degree polynomials. So this basically is the idea generated by x square plus 1. Okay. Once we introduce the notion of, so this map is also surjective, if you carefully notice. This map is in fact surjective, right? Because if you choose any element of the form a plus bi, then this will have the pre-image a plus bx, right? Yeah. So this map is in fact surjective, and once we study the first isomorphism theorem, it will be made clear that why does these exist. Okay, and we are going to prove that now itself. What I claim from here is that, so I got the kernel to be this. So what I claim from here is that Rx upon the ideal generated by x square plus 1 is isomorphic to C. Okay. In other words, I claim the following. Okay, this is a more general theorem. It will be applied over and over again throughout the course on ring theory. Theorem. and it's called the first isomorphism theorem. The first isomorphism theorem. It says that if phi from R to S is a ring homomorphism, then R mod the kernel of phi is isomorphic to the image of phi. Okay, fine. So this is the statement of the first isomorphism theorem. Okay, how do we prove this? Proof. The proof is quite simple. Proof. Take the map F. Okay, so I'm representing the kernel of phi by k. Okay, so take the map R mod k to the image of phi by mapping each element of the form R plus k to phi of R. Okay, then is it well defined? Let us first check that. Let R plus k equal to S plus k. So that would imply R minus S is in k. Now k is the kernel, right? So this implies that kernel of phi. So that implies phi of R minus S is 0. But that implies phi of R is equals to phi of S by the linearity of phi in terms of the addition. But that implies f of R plus k is equals to f of S plus k. Right? Therefore, this is well defined. Therefore, f is well defined. Now let's check whether it's injective or not. Now, f of R plus k, equals to f of S plus k. What does this imply? This implies that phi of R is equals to phi of S. This implies that phi of R minus S is 0. This implies R minus S is in the kernel. This implies R plus k is equals to S plus k. Right? So exactly the steps backward of well-definedness. Right? Is it surjective? What can you say? See, surjectivity is trivial, right? Subjectivity is trivial because if you choose any element from phi R, if S is in phi R, then this implies that phi R, then this implies that there exists some R in R, such that phi of R is equals to S. That means f of R plus k is equals to S. Therefore, the map is evidently surjective. And homomorphism property it holds trivially from the homomorphic nature of phi, right? So homomorphism is induced from phi itself, right? So therefore, we have an isomorphism. Therefore, R mod the kernel of phi is isomorphic to the image of phi. This actually gives us a very important set of statements as you observe immediately that therefore, if phi is surjective, right, then R mod kernel of phi is isomorphic to S itself, the whole ring S, the whole codomain S. Because in that case, image of phi will be the whole of S. And moreover, if phi is injective, then kernel of phi should be the trivial ring, then R would be isomorphic to S. Right? Okay. Clear? So this is exactly similar to the proof of group theory. Right? Okay. Fine. Let us check now some important examples of the first isomorphism theorem. Okay. Example. Okay. Claim if R is a ring and I is the ideal generated by X, then Rx mod X is isomorphic to R. Okay, fine. Is there some way to prove this? Let's see. Okay, so observe that to prove such a structure, first thing which one should think of is the first isomorphism theorem. Okay, and in order to have the first isomorphism theorem, what we require is basically the following. See what we want to do here is that let phi be a map from Rx to R such that f of x, let's evaluate it to f of 0. Okay, so what I'm doing is that I'm just evaluating every element at the 0 element. Okay, for example, if my f of x is x square plus 2x plus 3, then f of x will get mapped to just 3. Clear? Okay. So for you can observe that phi is a well-defined map. Okay, phi is well-defined. You can check on your own. Phi is well-defined. Okay, fine. Now, is phi surjective? Is phi surjective? Okay, such maps are basically called evaluation maps. Evaluation maps. Maps of the form phi taking any function, a polynomial typically, and it evaluating it to at some element is called an evaluation map. Okay, fine. Now, is phi surjective? It's clearly surjective. Why? Because Let us choose the element A in R, then the element A plus BX will evidently get mapped to A in R. Right. So we will obviously be having inverse images of every element in R. So it's a surjective map. Therefore, by the first isomorphism theorem, what we conclude is that R mod kernel of phi should be isomorphic. Sorry, Rx mod kernel of phi should be isomorphic to R. Now, what is kernel of phi? So by definition, kernel of phi is the collection of all those polynomials fx in Rx such that f of 0 is 0, right? That is phi of fx is 0. But phi of fx is 0 is same as saying f of 0 is 0. So it is a collection of all those polynomials which are having 0 as a root, right? And it can be evidently observed that then f of x should be of the form x times g of x, right? Clear? Because how can we claim this actually? What we can do is that you can just divide f by x. You will get a form of this plus some rx. Rx can either be x. Rx can either be of sorry, R must be of degree 0, right? What I'm trying to say is the following. See, if you divide fx by x, so you will get of this form, right? Fx equals to x times g of x plus r of x. But then a degree of r must be less than 1, right? So degree of r must be 0. So it must be a constant polynomial, right? It must be a constant polynomial. So if r is equals to c and f of 0 is equals to 0, then observe that r must be immediately 0, right? Everywhere r must be identically 0 because r is a constant map and r gets evaluated to 0, so it must be 0 every time. So if x will, so if f of 0 is 0, then f will obviously take this form. Getting my point? Fine. Therefore, every element in this set is of the form some multiple of x. So this should be the ideal generated by x, right? Therefore, what do we conclude is that Rx mod x is isomorphic. Sorry, Rx mod x is isomorphic to R. Clear? Okay. Now there are typically several other sort of these sort of what should I say, isomorphism theorems, typically speaking. So let us discuss a few of them. Okay. Okay. Let me take a new page. Okay. So this is something we call the isomorphism theorems. Okay. One of them is already covered, the isomorphism theorems. Okay. And these are basically every theorem which I'm going to write here are basically simple consequences of the first isomorphism theorem itself. Okay. Yeah. Okay. 1 second. I'm writing the statements. Okay. So number one, or rather number two, because this is called the second isomorphism theorem. Okay. It says that let A be a subring and B be an ideal of R. Then A plus B defined as A plus B such that A is in A, B is in B is a subring. A intersection B is an ideal of A, and then A plus B by B, because since B is an ideal, B is evidently contained inside A plus B, so B will also be an ideal of A plus B. So this is isomorphic to A mod A intersection. Okay. How is the proof? How can we come up with the proof? The proof you can do in this way. You can choose a map phi from A to A plus B by B, and if you carefully analyze the elements inside A plus B by B, you will observe that they are elements of the form. So I can just take A and I map it to, so it should be elements of the form A plus B. Okay. I guess it is itself the map you require, and you will get the kernel of this map. Suppose this map is phi, right? So you will get kernel of phi to be A intersection. Okay. Because see, by definition, the kernel should be the collection of all those elements A in capital A, such that A plus B is equals to B. So A must be in B. So I need to choose all those elements in A which are in B. So I need to choose the elements A intersection B. So it's, yeah, fine. Okay, so this is the consequence of the first isomorphism theorem. So then it's a surjective map. That's a very easy check. Then we have something called the third isomorphism theorem, which says that let I and J be ideals of R with I contained in J. Then J mod I is an ideal of R mod I, and R mod I by J mod I is isomorphic to R mod J. Okay, so this some sort of seems like division. That 2 by 3 by 4 by 3 is equals to 2 by 4, right? Yeah, and the proof of this is also pretty easy. You just need to observe carefully the things which are going on. Observe that. See, this is a pretty easy check, right? Wait a minute. See, this is a pretty easy check. right? Because if you choose an element of the form j plus I and you multiply an element r plus I to it, then it will get the element rj plus I, right? But j is given to be an ideal of R, so rj must be still in j, right? So this must be in j mod I, right? Pretty easy check. You can go for an easy check that this is an ideal, and the proof of this isomorphism, you can take the map phi from R mod I to R mod j, such that R plus I is mapped to R plus j. Okay, then the kernel of I will come out to be the collection of all those elements R plus I, such that R plus j is equals to j, right? So it should be the elements of the form R plus I, such that R is in j. So this should be exactly the coset j. Yeah, so the coset j model. Clear? Okay. Now there is another pretty important consequence of this the isomorphisms of ring, which is something which we call the correspondence theorem. Correspondence theorem. Okay. We will give a detailed proof of the correspondence theorem later. But what the correspondence theorem basically says is the following. Okay. It says that if I is a proper ideal in a ring R, then there exists a bijection from the family of all intermediate fields, sorry, of all intermediate ideals where I is contained in J is contained in R to the family of all ideals in R mod I given by J getting mapped to phi J, okay, which is just J mod I. Clear? Okay. Phi is the natural map. Okay. Okay. So we'll see a proof of this. Okay. Fine. So yeah, so let's give a proof of the correspondence theorem. So what we do is that let R prime be the set of all ideals, ideals of R. In fact, we can prove something stronger here. Okay, we can prove something stronger here. We will prove the following. Okay, and this will give the correspondence theorem as a corollary. Okay, so theorem: let f from R to S be a surjective ring homomorphism. So you can take f to be pi in the corollary. Then there exists a there exists a correspondence. Okay, between the set of ideals of R containing the kernel of F and the ideals of S. Okay. So for the corollary, you can choose F to be pi, S to be R mod I, and R as usual. So let's see. So proof, what we do is that let R prime be the set of all ideals of R containing kernel of F. Let S prime be the set of all ideals in S. Okay. Now let J be in R prime. Okay. Then J will be mapped to f of J under F, and an ideal I will get mapped to under inverse. It will get mapped to F inverse I. F is given to a surjection, right? So we can talk about pre-images. What is this set? So this is basically the collection of all the elements in R such that f of A is contained in I. Okay. So basically to show the correspondence, what we actually need to show is that F inverse of f of J is equals to J and f of f inverse I is equals to I. Okay. Right. Now some exercises I'll give here is the following. Okay. Exercise is that if F is a ring homomorphism, any ring homomorphism from R to S, then if I is an ideal in S, F inverse I is an ideal in R. Okay. And the second is that if F is a surjective ring homomorphism from R to S, so you should be making use of the subjectivity of what I'm gonna write now. Then, if I is an ideal of R, then its image is also an ideal in S. Yeah. Okay. To prove this, we will be requiring the subjectivity. Okay. We will be requiring the subjectivity. Fine. So this you can typically show very easily. Okay. That so what we are trying to say is that if I have an ideal I in S, then its inverse image will be an ideal under any ring homomorphism. If you have a surjective ring homomorphism, then images of ideals are ideals as well. Clear? Okay. Now, what more we can say is the following. Okay. Observe that in this case, F inverse I is not just an ideal. In fact, it's an ideal containing I. Why is it so? Because see, by what is the definition? See, by definition, F inverse I is a collection of all those elements A in R such that F of A is contained in I. Are you getting a hint of what I'm trying to say? Can you show that if I choose an element A from the kernel of F, then F of A must be 0, right? Since I is an ideal, so 0 will be in the ideal, so this must be in I. Or that implies that A must be in I. A must be in F inverse I, right? So this implies that the kernel of F, sorry, I wrote I there? No, not I, containing kernel of F. Okay. So kernel of F should be contained in F inverse I. Okay. Right. So what we have is that the above two exercises. That these are very easy exercises. Okay, just try them on your own. So what we have is that if I have an ideal in the codomain, then the inverse image is an ideal containing the kernel, and if F is a surjective homomorphism, then the image is also an ideal. Now what we show is the following. We show first that J is contained in F inverse F of J. Okay, where J is an ideal of R. Okay, sorry, this is something trivially observable. This is trivially true by the properties of maps and their inverse images. We need to show the reverse inclusion. This is what we need to show. Okay, so let's see. Suppose A is in F inverse F of J, and that implies that F of A is contained in F of J. So that implies that I can write F A is equals to F of X, where X is in J. But then that implies that F of A minus X is equals to 0. That implies that A minus X is in the kernel of F, but the kernel of F must be contained in J, right? Because what we need to show, let us just go back to what we need to show. We need to show that there is a correspondence between the ideals containing the kernel of F, the ideals containing the kernel of F, and the ideals in S. So I didn't write it here, but I assume J to be a kernel, J to be an ideal containing kernel of F, containing kernel of F, right? So from here it's proven, right? Right? Getting my point? Clear? Fine. So X was in J itself, right? So this implies that A itself is in J. I can just shift X towards J, right? Because X is already in J. So that implies that the reverse inclusion is done, right? So one direction of the correspondence is done. The other direction, what we need to show is that if I is an ideal in S, then F of F inverse of I must be contained in I. I guess this is again trivial due to properties of maps and inverse maps. I need to show I is contained in F of F inverse of I. Okay. How can I show this? If I choose an element A from I, now F is surjective in the hypothesis. So this implies that I can write A as F of R for some element R in capital R. But this implies that R must be in F inverse I, right? But this implies that F of R must be in F of F inverse I. But F of R is A, so A must be in F of F inverse I, right? Yeah. So just go through these statements very slowly, okay? Each and every statement very slowly. What we have shown is that there are so the corollary. Yeah. So what I was saying that just go through the statements very slowly, and you will get a hint of what I was typically trying to say about the correspondence. Okay. So as corollary, observe that if I choose the natural map R to R mod I via pi, I is a proper ideal of R, then via pi there exists a 1-1 correspondence between, see, the kernel of this map is I itself. Okay, so a one-one correspondence between ideals in R containing I and ideals in R mod I. In other words, typically what I'm trying to say is that typically J mod I is an ideal of R mod I if and only if J is an ideal of R containing I. Yep, got it. Fine. Right. So yeah, so we have discussed fairly a large number of things about uh, about ideals and quotient rings and homomorphisms. The next thing which I'm going to prove now, so now what we are going to, so we are going to move towards now analyzing ideals or analyzing domains and ideals and the interrelationships between them and so on and so forth. And now we are going to get into notions of a general notion of divisibility. In fact, like in the first lecture, in the introductory lecture on rings, we had discussed that a sort of a motivation of rings was generalizing whatever happens in the integers, and we know that divisibility is a well-known fact in integers. So we will be in some sense trying to generalize the notion of divisibility here in an arbitrary ring as well. Okay, so let us move on. Uh, So you can take this topic to be our now our main focus will be polynomials over fields. Okay, so we are going to consider those polynomial rings over fields. Now what we have previously concluded is that f of x is a domain when f is a field, right? But obviously f of x is not a field, right? This is an easy checking that the units in f of x are precisely, or in fact the units in Rx are precisely the units in R. Okay, you can just try and prove this. It's a very simple proof. Why is fx not a field? Because if you consider the element x in fx, then by definition of the identity or the unity element in fx, its inverse should be 1 over x. But that's not a polynomial, right? That's not a polynomial. Clear? Fine. So given f is a field, we are quite sure about the fact that it's an integral domain. That is, it consists of no zero divisors. The next thing enriches this property a bit. Okay. So theorem: if f is a field, then every ideal in fx is a principal ideal. Okay. So let's try and prove this out. The proof is fairly easy. Okay, just go through the steps which I'm trying to say, and the proof is actually very easy. Okay. So let I be an ideal in fx. Okay. Now if I consists of only the zero element, then I is simply generated by the zero element. Right. Therefore, choose I to be a non-zero ideal. Okay. Let mx be an element in I having the smallest degree. Why can I choose the smallest degree? Due to the well ordering principle of the natural, because the degree is a natural number, smallest degree. Okay. This is possible due to well ordering. Okay. Okay. We claim that I is generated by this polynomial itself. Another proof is actually very easy. Okay. See, let first thing first, since mx is itself in I, so by the closure property of ideals, the ideal generated by mx should be in I. Right. Now let qx be any polynomial in I. Divide qx by mx to get, so we are in a field, so we will get a unique factorization. So to get unique qx and rx such that I can write, okay, so let me make px, such that px is equals to qx times mx plus rx, such that the degree of r is less than the degree of m, or r is identically 0. No problem with that? Fine. So moving on to the next page. So therefore, this implies that px minus qx times mx equals to rx. Now observe that now px is an element of I by assumption, mx is an element of I by assumption, qx is an arbitrary element of rx or rather fx. Since I is an ideal, so qx times mx must be in I, since I is an ideal of R, I is an ideal of fx here, and qx is an arbitrary element of fx. But this implies that px minus qx times mx is in I, but this implies Rx is in I, which is a contradiction. Rather, not immediately a contradiction, I won't say it's immediately a contradiction, Rx is in I. Therefore, the degree of R, uh, it cannot be, or rather what I mean to say is that is the following. Therefore, R must be identically 0, right? Why is it so? Because as degree of R is less than M and M was assumed to be the smallest degree polynomial in I, right? So obviously there cannot exist a non-zero polynomial. See, whenever we are talking about polynomials, there is always a background assumption that it's a non-zero polynomial. If it is a zero polynomial, then what is the point of talking about that? So if R is a non-zero polynomial, then it cannot be in I because M is the smallest degree polynomial in I. So the only possibility for R to exist in I, because R will surely do exist in I, is that if R is exactly equal to 0, right? In that case, what we conclude is that Px is exactly equal to Qx times Mx, but Qx times Mx is an element of the ideal generated by X. So this implies that I is contained in the ideal generated by Mx, which implies I is exactly equal to the ideal generated by X. A similar proof will in fact show that all ideals, in fact subrings, in fact subgroups itself of Z are of the form Nz, which can be identified as the group or ring or ideal generated by X. There is no point of talking about subrings specifically, okay, because subgroups will do. Because if it's not a subgroup, because if all the subgroups are only of this possible type, then all the subrings should be of this possible type itself. Because for it to be a subring, it must at least be a subgroup, right? Okay. And so we have previously defined that a ring is said to be a principal ideal domain if every ideal is a principal ideal. So what we conclude is that if F is a field, Fx is a PID. Clear? In fact, whatever we stated here, that we can prove that every subgroup is of this form, so it will immediately prove that every ideal is of this form. Or if you do not want to get involved in the notion of subgroups, you can just do the same steps to prove that every ideal is of this form. Just choose I to be any ideal in Z and choose an element from I whose modulus is the least. Okay? Or you just choose the smallest positive element from I. Okay. Smallest non-zero positive element from I, that will do the trick. Okay. So this in fact also say that Z is a PID. And we have already proven that Zx is not a PID. Recall that 2x was an ideal in Zx, right? Which was not a principal ideal. So these sort of questions often come in interviews, PhD interviews or master interviews. That if R is a PID, then Rx is a PID. Is it true? It is not true. Z is a counter example. That Z is a PID, but Zx is not a PID. While if F is a field, if R is a field, then we are sure that Rx is a PID if R is a field. Clear? In fact, we have also proven a bit previously, I guess in a previous lecture itself, that if F is a field, then every element in f of x has a unique factorization. And this will be made use a bit later when we will be talking about Euclidean domains and unique factorization domains. And in between will come the principal ideal domains. We'll see that. Nothing complicated. Now, as I said that, let us move on to the notions, the general notions of divisibility. Definition. Let R be a ring. Okay. If R and S are in capital R, we say R divides S, denoted as R divides S, if there exists some R prime in R, such that R times R prime is equal to S. Right? It can be easily observed from here is that R divides S if and only if S is in the ideal generated by R. Right? Okay. In fact, we can also observe that R divides 0. Every element in a ring will divide the 0 element. Right? But 0 divides R if and only if R is exactly equal to 0. Right? it seems to be a bit non-trivial that 0 divides something, but it abides by the definition. Okay, because 0 divides r, that would imply, what does this imply? This implies that 0 times something would be equal to r. So that means r is equal to 0. And if r is equal to 0, then the idea is generated by r is the 0 element, so 0 is in the ideal. So yes, I mean r is in the 0 ideal, so 0 must divide r. Right? This implies that r is in the 0 ideal, so that implies 0 divides r. Yeah? Furthermore, clearly, by the same definition itself, that r divides 1 if and only if r is a unit. Right? If and only if the idea generated by r is the whole ring. Right? Because if r divides 1, there exists an element such that r times that element is 1, so r is a unit. Right? And if r is a unit, then there again exists an element such that it goes to 1 multiplied when with that element goes to 1, so it divides 1. Right? Okay. Now here, actually, we can have a general notion of a greatest common divisor. So this is the last thing I'm going to talk about today, the greatest common divisor. Okay. So let R be a domain, and let fx and gx be in Rx. We can define it for typically for any arbitrary ring as well, but there will be a question of it existing or non-existing. Since we are talking about commutative rings with unity, it's better to leave those topics that when the GCD exists or when it does not exist. When we will be on the verge of completing the course, there will be several ideas which will automatically answer us that when does these exist or these not exist. For now, let us just assume R to be an integral domain, and let us choose two polynomials from Rx. Then the GCD, that is the greatest common divisor of fx and gx, is a polynomial dx in Rx such that number one, dx divides fx and dx divides gx in Rx. Fine. Number two, that if cx divides fx and cx divides gx in Rx, then cx must also divide dx in Rx. And number three is that dx is monic. Clear? So this is the basic definition of the greatest common divisor, and we say that f and g are, or rather, we say f and g are co-prime if and only if their GCD is 1. Okay, clear? Fine. So we can in fact prove, okay, this will be a topic of the next lecture, that if I have a field and I take the polynomial ring over that field, then if I choose two polynomials from that field, then I can write the GCD of those polynomials as a linear combination of those polynomials, just as we can do in the case of integers, right? In integers, recall that given two elements, we can, so recall that if R and S are two integers and D is the GCD of R and S, then there exists x and y integers such that Rx plus Sy is equals to D. We can do the same in fx when f is a field. Okay, so that will be a topic of the next lecture. So meet you guys the next time. Okay, we are almost on the verge of completing this lecture. There will be, I guess, two more lectures where we talk about, we haven't yet talked about prime ideals and maximal ideals. We need to talk about those. We need to complete this part of the general notions of divisibility, and then we need to go into the PIDs, UFDs, and then the irreducibility of polynomials, so on and so forth. Okay, fine. So meet you guys in the next lecture.